Now that we understand how two-side periodic lattice work, let us jump to n-side periodic one-dimensional lattice. In other words, endpoints on a ring, and we have coordinates 0, 1, 2, 3. So what does the shift operator does? It just moves like a clock everybody, the fields on each side by one step. And after n steps, we are back, tuk, 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 tuk. In other words, the characteristic equation for the shift operator is very simple. I repeat it n times. This is a matrix. And I get a unit matrix, which is n by n unit matrix because that's how many sides are. Now we know how to solve this equation. This is the matrix, but we can just take number x, raise it to n to find the powers. So what are the eigenvalues? There's an obvious one. It's omega, a complex number, which is pure phase, meaning it has magnitude 1, and it's I 2 pi over n. So that's clearly something that we multiply by itself n times, we get unity. But there should be n roots of unity, it's nth order polynomial. And what are those? Put 1 on this side, so it's assuming n equals 1. It's a matrix, satisfies its own characteristic polynomial, how many roots it has. If first root is labeled 0 in all the n minus 1 roots, these are just points on a circle in a complex unit circle in a complex plane, which is this simplest possible root to the power k times unity. We have n distinct eigenvalues, and we have now an n-dimensional space we started with, and it will have n eigenvectors. We have n irreducible representations, if you want to think of group theoretic language. Now remember, with each eigenvalue and eigendirection comes a projection operator. There are n distinct eigenvalues. So there are n projection operators. And the way we like to write projection operators of a matrix is we take all terms in this product. So we take sigma minus omega to the j times unity. So there's a product. And then we remove a single term in this product that corresponds to eigenvalue k. And then we normalize it all correctly so that this operator square is idempotent, it's itself. So these are projection operators. Usually you won't see them in this form. You can rewrite this as a sum. It's an exercise in the book. You take any matrix function of this matrix. So this is any function. If this is a scalar, this is a scalar, but this is now a matrix function, n by n. And if you multiply it by projection operator k, this thing can be a horrible matrix. I'll show some examples with lots of entries every place. N times n dimensional ugly matrix. But now that we have projection operators, we know that on each subspace, this whole matrix simply gets replaced by the function of a single number, which happens to be this primitive root of unity raised to the power k. So we reduced a big matrix to n numbers.